Our third of the combined gas law is also known as Lussacs Law. And that's a correlation between pressure and temperature. P1 over T1 equals P2 over T2. And this is very similar to what we saw with Charles' law in that this is a direct relationship. Okay, a direct relationship. So as one goes up, the other goes up. If I take pressure and multiply it by 2, then my temperature is going to go by 2. If I take pressure and reduce it by 1/4, my temperature is going to be reduced by 1/4. Now, sorry, we're going off the video there. One of the things you have to be conscious of, just like we saw in the Charles law examples, is that you must use Kelvin temperatures, because again, a doubling in Celsius is not the same thing as a doubling in Kelvin. So if we look at our first question, an automobile tire has a pressure of 198 kPa at 20 degrees Celsius. What will be the pressure after driving if the tire temperature rises to 80? So this is multiplied by 4, but it's really not an increase in 4 times the value. So just like I showed you in the other video, if we start from 20 and we go to 80, that's like multiplying by 4, but if we do the math, really that's an increase or a change in 60 degrees Celsius. If we do the conversion, again, my formula K equals degrees C plus 273 to convert. If I plug that in, if I plug in 20 degrees, we get 293 Kelvin. If I plug 80 in there, 80 plus 273 is 353. So if I go from 293 to 353, that also, if we do the math and subtract, that's also a change in 60 degrees, now 60 Kelvin. But that is not, okay, is that a times 4 value? To go from 293 to 353, absolutely not. That's not 4 times. That's why we have to convert, because a difference in temperature is the same, but a doubling of temperature is not, between Celsius and Kelvin, Kelvin and Celsius. Okay, those are two very different things. So again, anytime that you do Charles' law and Gay-Lussac's law, or the combined gas law, which puts all three together with Boyle's law, then what you have to do is use Kelvin temperatures. Okay, you have to use Kelvin temperatures. So we have our three numbers here. My initial pressure is 199 kPa. My original temperature, we converted 293 Kelvin. What will the pressure be? So we're trying to solve for P2 if the temperature goes to 353 Kelvin. And just like we saw in one of the last examples for Charles' law, we're going to do the same thing. If we want to get rid of an unknown, fortunately, or solve for the unknown, fortunately, I think my equal sign stand out a little bit more there. Fortunately, what I'm solving for is at the top in the numerator, so the math is going to be a little bit easier, less steps. I'm going to multiply 353K on both sides. So I can get rid of this on the right side, and then my K's cancel out, and I'm going to be left with kilopascals, kPas, which is my unit, because I want to solve for pressure. So in my calculator, 353 times 199 divided by 293, P2 is equal to 240 kPas. Now, look at it proportionally. Temperature went up, 293 to 353. So if temperature goes up, pressure should go up, 199 to 240. Okay, this one went up a little bit, that one went up a little bit, from 199 to 240. All right, number 2, a cylinder of helium outside in the sun has a pressure of 2,000 psi and a temperature of 51 degrees Celsius. If the cylinder is taken indoors and cooled to 20 degrees Celsius, what will its new pressure be? PSI is pounds per square inch. That one's not on your reference table for New York State, but it is just another thing that you should become familiar with. So if you're filling up a bike tire, or if you go scuba diving, or if you know someone who's a firefighter, all those things are in pounds per square inch. If you fill up your car tire, those are pounds per square inch. So we have our numbers, and we also, again, we have to convert. So 20, easily enough, like we had in the previous question, is 293K, and then 51 is going to be, I'm just going to write it down here, is 324K, because again, I'm just adding, I'm taking the 51 and I'm adding it into my formula. 51 plus 273 is 324. So I have my three initial numbers. There's my 2,000 psi. So I want to know, I'm going to solve, what will the new pressure be? So again, I'm solving for P2. So we have 2,000 psi originally at 293, sorry, making sure we're using the right numbers here, Make sure we read it in order. It started at 51, so that's my 324 value, 324K. And it said also, another hint, it said it was cooled. If it's cooled, then of course we're going down. So my second temperature was 293K. We want to know what P2 is. Now think about a balloon, or a basketball or a football or even a water bottle or a gas tank that's been outside in the winter and it's cooled overnight. When you go out and look at it, it actually shrinks. It kind of basically compresses in. And so there's also changes in the pressure too. Not only is there changes in volume, but there's also changes in pressure when you try to open that up. And so the pressure decreases. Sometimes it's a little bit harder to open that up. And so again, we're going to do the same thing as we did in this question, because what we're trying to solve is on the top. I'm going to multiply by 293K on the top and 293K at the top. My K's cancel out, 293's cancel out. 293 times 2,000 divided by 324, in this case, is going to be 1809 PSI. Okay, that's what my P2 is. My temperature went down, 324 down to 293. So my pressure, good check to make sure that your answers make sense. My pressure from 2,000 down to 1809. All right, let's solve for one that's in the bottom. We haven't seen this one yet in a couple examples. What temperature must a sample of nitrogen gas at 22 degrees Celsius and 0.7 atmosphere be heated to so that its pressure increases to 1.25 atmospheres? So again, I have to change, and now we're solving for temperature. So 22, I'm just going to add 22 to that. So basically we have 295K. And when we plug this in, to what temperature? To what? That means what I'm going to go to, that's what I'm going to solve for. So I'm solving for T2. Okay, I'm solving for T2. T1 is 295K. My initial pressure is 0.700 atmospheres, ATMs, and I go to 1.25 ATMs. Oops, ATM. Now generally, we know that the pressure is increasing, so my temperature should also increase. When I go to the final answer, it should also increase. Now, this is almost a doubling. If I were to double 0.7, I'd get 1.4. So this is almost a doubling. So when I go and look for my final answer, this should almost be a doubling as well. This is 295. It's close to 300. So my answer should be less than 600 if I were to double it. But again, it should look like it's close to 600. So I still have the same process. I'm going to cross multiply and divide, but I want to solve for T2 now. So if I want to get T2 by itself, okay, there's multiple ways you can do this, and you might know an easier way, or it's simple for you. And again, one is not better than the other. You could do a series of steps and make it, or you could, sometimes if the state just shows and asks for the numerical setup, this would be your numerical setup and you would be done. You wouldn't have to do anything else. But in reality, I still got to do the same thing. I got to cross multiply and divide. So if I'm going to cross multiply, and if I want to bring up T2 on both sides, times T2 here, times T2 here, then basically I've gotten rid of T2 on that side, but I still now have all this. So I got to bring that whole thing over here as a reverse. I got to flip it. I got to do 295K over 0.700 ATM, because I'm going to flip. I'm going to do the reciprocal. Just like if you did it over here, if I want to get rid of this, I got to multiply by 295K, because that's in the numerator, so I got to multiply it. Because the 0.7 was in the numerator, I got to divide it, 0.700 ATM. So I just did the reverse. So my ATMs cancel, my Kelvins cancel. Now I'm left with T. We get 1.25 times 295 divided by 0.7. Again, ATM on the top, ATM on the bottom. If you have two things with the same unit on either both the top or both the bottom, then you know you've done something wrong in your conversion and your setup. And so finally, when all is said and done, T2 equals 527K when I take 125 times 295 divided by 0.7. And so from originally 295 to 527, that is almost, it's getting close to a doubling. Doubling would be, 590. So it's not a complete double, but it is a double. So very similar to Charles' law, Lussacs Law, or with temperature and pressure relationships, is also a direct relationship law and direct relationship scenario. So if one goes up, the other goes up. If one goes up by a multiple of 100, the other goes up by a multiple of 100. If one gets divided, or reduced by a value of 50 or a fraction of 50, then the other one gets reduced by a fraction of 50 or reduced by a value of 50. So hopefully you found some value in this third of the combined gas laws, and we look forward to seeing your success. If you have questions, you can always leave them below.